Okay, we're in chapter J, and we're going to do here the derivative of the cosine and the tangent. Now, in the previous class, we looked at a plot of the sine and the cosine. And we saw that the derivative of the sine is the cosine. In other words, the slope of the sine at 0 is 1. And then the slope up here is 0, and there's your cosine, 0. And the sine at pi, the slope there is a minus 1, which is the cosine minus 1. Now let's look at the reverse. Let's look at the derivative of the cosine. Well, the cosine here has no slope, and the sine is 0. Let's find another place where there's no slope for the cosine. That would be here, and the sine is 0. What about these other points? Well, here it looks like the cosine has a negative 1 slope, possibly, and the sine is 1. Well, that's opposite. So maybe the derivative of the cosine is a negative sign. Let's check this other point here. Here the cosine looks like it has possibly a positive 1 for the slope. And if you slap a minus sign on it, you get the minus. That's what the sine is. So maybe, and we're going to show you this is the case, the derivative of the cosine is going to be negative the sine. Now we would like to do this here in a short way, and there was a lot of stuff we had to do when we did a derivative of the sine. But the cosine will actually be easy. And the reason why is a nice relationship. If we look at our right triangle and say we have an x here, the angle up here is pi over 2 minus x. That's this angle up there. These angles are complementary. When you add them together, x plus pi over 2 minus x is pi over 2. And that is 90. And that 90, with this 90, gets you to 180 that you have in a triangle. Let's make this hypotenuse 1. And let's look at the base. The base here is the cosine of x, since the hypotenuse is 1. And this is also the sine of this angle, since that's the opposite side. So it's also the sine of pi over 2 minus x. Here we have the altitude of the triangle, and the altitude would be the sine of x, since we have a 1 here, 1 times the sine of x, so that's the sine of x. And for this angle, it's the adjacent. So it's the cosine of pi over 2 minus x. So we have this nice relationship, which we have seen before, that if you have the cosine of an angle x, it's equal to the sine of the complement, pi over 2 minus x. And the same, if you have the sine of x, it's the cosine of pi over 2 minus x. So here, we're going to take the derivative of the cosine. I want to find out what the derivative of the cosine is. And that's going to be the derivative with respect to x of sine pi over 2 minus x. Now I'm going to use the chain rule. I'm going to let this equal u, and then take the derivative of the sine of u with respect to u first, and then go du dx using the chain rule. So we have here sine of u, and d dx of that would be d du of that, then times du dx. Now, du dx is very easy. Look at this. U is pi over 2 minus x, so du dx equals, well, that's a constant, so that would give you 0 on the derivative, and that's just going to simply be a minus 1. So this is going to be a minus 1, and the derivative of the sine with respect to u, we already figured that out. That's the cosine of u. So this is minus the cosine of u, but we're not finished yet because we would like to express that u in terms of x, since we started with x here. So we're going to go ahead and put this in. So this derivative is going to be equal to minus the cosine of u, which is pi over 2 minus x. All right, but now we know that the cosine of pi over 2 minus x, that quantity, that's simply the sine. And we have shown what we thought might be the case, that the derivative of the cosine is minus the sine. So, quite a short derivation compared to all the steps we did for the taking the derivative of the sine. So let's go ahead and write this result down. The derivative of the cosine of x is minus the sine of x. That was short, and that's so short that I'm going to go ahead and do the tangent while we're at it. So let's look at the tangent. The tangent of x is the sine of x divided by the cosine of x. And what I would like to do is use the product rule. You know, I don't really like the division rule for derivatives since I have trouble remembering it. So here we're going to have the sine times the cosine to the minus 1 power. So we basically have sine of x times 1 over cosine of x. I like to write that minus 1 out here because if I put the minus 1 inside, that's going to indicate inverse arc, or an arc. We don't want to mess with that. So this is clearly what we have. And for the product rule, when we take the derivative, say, and I'll go ahead and write this out, the derivative of the tangent with respect to x, it would be the derivative of the first. Go ahead and write that out. The derivative of the first times the second, which would be cosine of x to the minus 1, plus the first function times the derivative of the second. Let's go ahead and just really put the brackets down, make sure there's no confusion on notation. Now, the derivative of the sine, we already know, is the cosine. And when we multiply the cosine of x with 1 over the cosine of x, we're going to get 1. Now over here, what I'm going to do is kind of a chain rule thing. I want to bring that minus 1 down. In other words, this is going to be done as minus 1 times the cosine of x to then the minus 2 power. So we're looking at this as a power, like u to the minus 1. And then I need to take the derivative of what's inside. And what's inside is a cosine of x. And if I take the derivative of the cosine of x, I will get minus the sine of x. Now, minus the sine of x will cancel this minus sign, and with the sine of x here, we'll have sine of x squared over cosine of x squared. All right, that's saying a lot. So let's go ahead and write this out as the sine of x, leave that alone. and we'll go ahead and put here a dividing sign like this. And here, what we should do is go ahead and put that minus sign of x in here, so we do have it completed. So the derivative here, you bring the minus 1 down, cosine of x to the minus 2, and the derivative of what's inside. All right. So then we could see that this minus sign cancels that minus sign, and we'll have an extra sine of x here. And then in the denominator, I'll have the cosine of x here, and that's going to be squared. All right, if you want, we could put parentheses or like that. I want to talk a little bit about this let u equal something when we take derivatives. For example, we just looked at taking the derivative of the cosine of x to the minus 1. And what I did is I pulled the minus 1 down using the chain rule. So you take the derivative of this power using the power law. So this is going to be minus 1 cosine of x. And then this is going to be to the minus 2. You subtract 1. And then you take the derivative of what's inside, which is going to be the derivative of the cosine, which is minus the sine. Now, this is what we did, but when I was studying calculus many years ago, they would do this let u equal a lot. In other words, they let this thing here inside equal u. And they would say just let u equal cosine of x. Now, I don't think we, in practice, need to do this. Maybe at the beginning, I prefer just to do what I just did here. You bring the minus 1 down, you have then cosine of x to the minus 2, and then you take the derivative of what's inside. We're done. But let me show you that this is, when I first studied calculus, I would see this a lot. So then this becomes d dx of u to the minus 1. And then what you do is you write this as d du of u to the minus 1, and then du dx, the chain rule, explicitly written out in detail. Then you bring the minus 1 down. I'll put the minus 1 there to emphasize it. And then there's going to be u to the minus 2. Then you're finished that part. Then you just have to do the du dx. And since the u is cosine of x, the derivative of the cosine of x with respect to x is minus the sine of x. Now you see, we essentially have the same thing because the u is cosine of x. When you put that cosine of x, and you get this. But it's easier in practice, when you've done this the long way, to just say, bring the minus 1 down and have cosine of x to the minus 2, and then take the derivative of what's inside with respect to x. And we're just finished in one line rather than having to say let u equal cosine of x, etc. So in the future, I'm going to be doing this the quicker way rather than, always going to let u equal something. So what we have here is going to be the sine squared over the cosine squared. So that means for our derivative of the tangent of x, and I'm just going to go ahead and use the abbreviation here, the derivative of tangent is going to be 1 plus the sine squared of x over the cosine squared of x. And we usually put that 2 inside like that when we're doing squares. Now, we can find a common denominator here. And the common denominator is the cosine squared of x. So this would be cosine squared of x plus the sine squared of x all over the cosine squared of x. All right? Cosine squared of x divides into there to get you to 1, and then sine squared x over cosine squared x gets you that one. And this is 1 over the cosine squared x. Now you're going to see that is the secant squared. A secant doesn't do much for me. I want to focus on this form here because I want to graph these. I want to do some sketches. So we want to sketch the tangent of x first. Let's go back. Let's just say, what does this tangent of x look like? And then see if the slope of it would be equal to 1 over the cosine squared. All right. Well, for the tangent of x, let's go ahead and put here some axis. And we'll have, this is 0. This is the x-axis here. Okay, so this is 0. And we'll have somewhere here a pi over 2. And we'll have a pi. So let's just do some of the sketching. Now, when you look at the tangent of x, and if we just go ahead and just have a little reference here, like here's the x. The tangent is the rise over the run. So when x is 0, well, tangent's 0. So that's going to be here someplace. Well, 0, it's going to be there. And then if you look at pi over 2, when this swings up to pi over 2, the tangent goes to infinity because, the run is going to 0. So that means if we have say a dotted line here like this thing is going to go off to infinity. Then when you have this circle here, and you're looking at, say, going beyond that. So now when you look at your rise over your run, you're basically going backwards. So you have a negative infinity. That's going to be way down here. And then you're going to come up as you approach pi, it's going to be 0 again. So you're going to go from here back to 0. But what's going to be here? Is it going to slide down and be a minimum, or is it going to slope down and have some slope? So let's look at that. If the x is small, then we know, since the tangent of x is the sine of x over the cosine of x, we have looked at this before in a previous chapter. We have a very, very small x that the arc here, which is x, since we have a 1 for the radius, and remember your arc length s is always equal to the radius times your angle theta. Well, here the angle is x, this is x, r is 1, so this arc is x. And you see this is the height here is the sine of x, and the sine of x starts to look very close to x as we go in the limit. So this sine of x is approximately x. And the cosine of x, which is this line here, that doesn't quite go out to the 1, because this radius is 1, that cosine of x is approximately 1 as we get smaller and smaller. So that means the tangent of x is approximately x. Now x has to be in radians, but this is very, very good to know because that's a simple straight line. Y equals x. It's a straight line. It's got slope 1. So then I can complete, and go on either side there. So this one's going to come up, and when it crosses, it's going to be 1. Now let me show you that, because it may not be obvious that on the other side, the slope would still be 1. So if we look at that, let's draw another picture here where we have a big angle that's almost at pi. All right, now let's call this angle in here alpha. And the arc here would be alpha, that little piece. So here, the tangent of alpha, since alpha is small, would be alpha. We're just applying this again. Now, when you have that alpha there like that, you really need to just simply take the, for the sine, the opposite side here over the 1. But when you're looking at x, like this angle, then the cosine is negative. Because see, then you would have to come out here as a negative. So let's look at this carefully. The sine, let's do them separately here. Where this is the x. So how do I handle that sine of x? Where it's almost pi. Well, this sine of x is going to be the same as the sine of alpha. And that's positive. So this is going to be equal to the sine of alpha. When you have supplementary angles, or two angles equal 180, the sines are the same. And you can see it here. It's going to be the same height. And that's going to be approximately equal to alpha. Now the cosine of x, where now x is the big angle that's almost pi, that's going to be equal to minus the cosine of alpha. So the cosine of alpha, see, is this distance here. And since it's in a negative direction, when you're referencing it to this angle, it's a negative cosine of alpha. And that's going to be approximately, since when alpha is small, cosine is approximately 1. So this is approximately minus 1. All right. Now that we have that done, let's look at what happens when we're near pi. When we're near pi, then the tangent of x is going to be the sine of x over the cosine, so it's going to be negative alpha. And let's remind ourselves that x plus alpha is pi. So since x here, if we're going to make an equation, x plus alpha is equal to pi, which means that from here, that the alpha is equal to pi minus x, and the negative alpha would be x minus pi. But see, now you can see we have a straight line again, with the slope is 1. That's an equation of a straight line, y equals mx plus b, where the slope is 1. So that justifies here that this is a 1, and that's going to go up, go up like that. But I want to focus on 0 to pi, and I want to check to see that at least the slopes with the 1 over the cosine squared seem to agree with this. So for that, I'm going to look at another little graph here. And we'll go ahead and put in here the pi over 2. And we'll go ahead and put in here the pi. And when you have 0, say, here you have 0, what is the slope predicted by the 1 over cosine squared of x? You just go ahead and write down here the tangent, the derivative of it, is equal to 1 over the cosine squared of x. So I have it right here next to the graph. So when the cosine squared at x equals 0, well, at x equals 0, the cosine of 0 is 1. You square it, you get 1. So that means you're going to have a 1 here. And that's good, because that's what the slope is up in here. It checks out. And what about at pi? Now see, here's important to have that squared, because the cosine of pi is negative 1. But if it's squared, you get plus 1. And 1 over 1 is still 1. So that's over here. That's going to be up here again. And that's what we have. Slope is 1. Slope is 1. Well, what happens when we have pi over 2, well, see, when the cosine, when you go to pi over 2, remember for your cosine, I'm going around like this, your cosine, when you go to up here to 90, the cosine is going to 0. Well, that means it's 1 over something real small, so that is heading up there to infinity. And then notice that when you go beyond pi over 2, the slope is still positive. Well, see, if you go beyond pi over 2, the cosine would be negative, but if you square it, it's positive, and you're dividing by it. And it's real small, and it's going to be a positive, and when you divide by a small quantity, you're going to have, say, the infinite result, and this is going to then come down and come in there like that. You might say this is the secant squared, but I don't really, in my mind, remember what the secant graph looks like. So I like to work with the cosine. So remember, it's always important to have a picture when you're doing derivatives so you can just compare to make sure things look like they should. So I'm going to box this off, that's our conclusion. But since most books are going to put the secant square there, I'll go ahead and box that one off also. That the derivative of the tangent is the secant square, which I like to think of as 1 over the cosine squared as I analyzed it. Well, we'll see you next class.